Okay, can everyone take a seat, please? Okay, we're about to get started. I'll let you just settle down. Okay. It's all right. Oh, did you get some notes? Have you already got some? Fine. Okay. Right. So, welcome everybody to optics. So, this is the first part of a two-part course. This part is going to be on geometric optics, and that's going to take us the next 6 lectures or so. I think it probably will take the full 6 lectures. And then there's a second part on wave optics in Hilary term. It's not until the end of Hilary term, actually, so this course is split into 2 quite distinct parts. So why study optics? So something you'll probably quickly learn, and it's not just here, I promise, is that pretty much everybody hates optics. So why do we make you study it? Well, actually, there are very good reasons why you should study it. And the first reason is its central importance in history. So this is Newton, and he was famous not only for his mechanics, which I'm sure you are very well aware of, but also for his optics. He went against the trend, and he actually really loved his optics, actually. He spent many, many years of his life doing all sorts of experiments, making deductions, and it really probably one could make a reasonable argument that for much of its history, physics was pretty much nothing more than the study of mechanics and the study of optics. So it's not that surprising that a large part of your first year is devoted to studying these things. There's also its role in technology. So optics has really dominated technology in physics anyway, since the invention of the telescope and then through to modern day, where it has all sorts of applications in communication, in the internet, in medical devices, in security and national defense, and the list goes on. And we're going increasingly now from an age dominated by conventional electronics to one where electronics and optics is combined into a single technology, and that's quite a hot topic at the moment. There's also its simplicity. So it's quite easy to at least understand the basic way things work. So probably when you go into labs and you try and set up some optics experiments, you'll actually get quite frustrated because actually getting it to work properly actually can be a bit tricky. And also if we were to do all of the maths rigorously and properly, it also gets very complicated. But you'll see that the best way to do optics to understand basically the way things work is to make certain approximations, and in that sense it's quite simple. And you can also demonstrate to yourself pretty much all of what I'm going to say with some very simple equipment that you might even have just lying around. Some of what I'm going to say you can just stare out of a window to sort of prove it to yourself. And if you're willing to spend £10 on a laser and maybe a lens and a mirror and a prism or something, then you can demonstrate to yourself essentially everything I'm going to say in this part of the course. It's probably worth remembering as well that Newton himself pretty much made all his deductions just by use of a hole in his curtains, a few prisms, and a quite terrifying willingness to poke at his eye with needles. You can go away and read about that if you don't know about that. There's also its centrality as well. So this is a picture of picture from a recent branch of physics, relatively recent anyway, called atom optics. So just like a light beam, beams of atoms display features such as interference and diffraction. So understanding the way light behaves actually gives you a very good basis for thinking about the world. It gives you good preparation for thinking about quantum mechanics later on. And then, of course, you've got to pass CP2, whether you like it or not. So not a lot of choice. You have to study this. Okay, so this is my disclaimer right at the start. So there is a bit of a problem with teaching this level of optics, first year optics. All of you will have very different backgrounds. Some of you will have done a lot of optics before at A-level. Some of you may have done almost none. And we find this every year. It's very, very difficult, I think, impossible almost to keep everybody happy. So this is summarised by some, feedback to the lecture a few years ago, where someone quite reasonably complained it was all too much A-level content, I knew it all, and, can't we do something else? And then someone else sitting in the exact same lecture course saying it was all horribly complicated, I didn't understand anything, can't you start from the beginning? So it is a difficult problem. This course is supposed to be a basic one. It is supposed to get everybody up by the end of the year to the same level, and then you will do a slightly more advanced optics course next year. So that's my disclaimer. I'm sorry if you find it all basic, but if you do, then you should sit back and be happy that you have 40% or so of CP2, maybe not quite, 35% of CP2 exam already in the bag with absolutely zero effort. So you should be happy rather than upset. Okay, so a few preliminaries first of all. So this is my teaching website. On here you will find full copies in colour of these lecture slides. You'll find a copy with, sort of full size, one slide per page, and also a colour version of what you probably have in front of you of 4 slides per page. Is there anybody that doesn't have notes and would like some? Because there's a few spares at the front. If you could put your hand up if you've not got any. Okay, so I'm just going to, the reason I've given you copies, right, this is quite a descriptive course in many ways. So I've had feedback before that people appreciate having the hard copies of lectures, because a lot of what I'm going to do, I won't be writing on the board continuously. What I will do is do all mathematical derivations on the board to slow us down, to do it in real time so that you can then copy it down, because in those notes there are some, as you'll see, some blank spaces that I've just left for us to do that, for you to fill it in, to sort of keep everybody awake, essentially. But there's also a lot of descriptive stuff where I won't be writing it on the board. But what you might want to do, and this is why you've got this copy, is sort of supplement what you've got in front of you with things that I say, and add notes. However, I am aware that some people may not want a hard copy, so if that is the case, that is absolutely fine. As I said, they're all available on my teaching website. If you don't, then feel free to give them back to me at the end of this lecture or tomorrow, however long it takes you to decide, and I can use them next year. That's absolutely fine. But if you do that, please don't write on them today because I'll want them nice and clear and blank for other people later on. But you're very welcome to keep them. It's up to you as to your preferred way of doing things. Okay. Also on my lecture website, you'll find problem sheets. There is just one for this part of the course, which is clearly labelled Geometric Optics. And then there's another one, it's already up, but that's not until Hilary term. And then you'll find a syllabus and further reading as well. Okay, here's a summary of the syllabus. I mean, I won't particularly talk about this too much, but this is just to give you a guide of what we're going to talk about. So we'll basically talk about reflection, refraction, the basics of lenses and mirrors and how they work. And then I'll spend one lecture as well just talking about some more practical bits of optical equipment, so telescopes, microscopes. And what you'll see is that bit is non-examinable. So I think that will probably be the 6th lecture. Maybe I'll get there just at the end of the 5th, we'll see. So it isn't examinable, as I say, unless the examiner forgets. Hopefully that won't happen for you. But it is still worth knowing because it's knowledge that will be assumed in your 2nd year and will not be done again, right? So it is still worth paying attention to. It's not your highest priority for revision, but perhaps over the summer you look at it again, ready for next year. Okay, so what is geometric optics? It's a simplified branch of optics, basically, where we describe the propagation of light in terms of rays of light. So we ignore wave-like features such as interference and diffraction. That's what we will cover next term. But it's a very useful approximation in many cases, particularly, basically, it's a very good approximation if the wavelength is much less than the size of the structure with which light is interacting, so a lens or a mirror, whatever it might be. That's when it's a really good approximation, and therefore it's a very useful branch in understanding how lenses and mirrors and therefore bits of optical equipment such as telescopes actually work. So I'm going to start today, and it's probably going to, I don't know, maybe take the next 15 minutes or so, we'll see, with a little bit of a historical introduction just to set the scene. This is quite a gentle first lecture. I don't think you'll be writing too much today. I think maybe we'll get to 1 or 2 proofs. I'll then start talking about reflection and refraction, and we'll derive the laws of reflection and refraction in two different ways. One using Huygens principle, which I suspect the majority of you have heard of, certainly if you did study optics at A-level, and then we'll also do it using Fermat's principle. And that's going to then lead to a couple of important concepts, the critical angle and the idea of total internal reflection. That'll lead us on to lenses, the concepts of real and virtual images, and we'll derive the thin lens formula, then mirrors, and then, as I said, talk a little bit about telescopes and microscopes. Okay, so let's go back in history to around 1700. So at this time, there was a lot starting to be known about how light behaves, but not much about why it behaves as it does. So Newton published his Optics in 1704. This was basically a collection of his experiments and deductions he'd made from them. Actually, he had this ready quite some time before, but he delayed the publication until 1704, until after the death of Robert Hooke, because they had a big, well, you know, they didn't like each other at all. And Newton had become very, very sensitive to any criticism by Robert Hooke, and Newton was a big advocate of the particle theory of light, of a particle theory of light. Hooke was on the other side with a wave theory of light. Newton was very, very sensitive to any criticism, and so he didn't want to publish this and potentially get criticism from Robert Hooke, so he sort of delayed it. Newton wasn't really a very nice man, by all accounts, very brilliant, but not very nice. He had a lot of petty vendettas with lots of people, and could even be argued that he probably held back physics in some ways by about 100 years just by these personal arguments. But anyway, he was a brilliant man, nevertheless. So you may or may not know that one of the biggest arguments in physics at the time was whether light was waves or was it particles. So this might seem like quite a modern issue, but actually it really dominated physics in the 18th century. And there were great advocates on both sides. So the reason it was such an argument, such a problem in people's minds, well, the arguments went something like this. So light travels in straight lines. We know that. Newton sort of proved it to himself just by using a hole in his curtains, looking at the way that a spot of light moved around on a piece of paper. We know it from the way shadows are cast. Nowadays, of course, I can just shine this laser over there, and you know, if my hand wasn't wobbling, it would be just going in a straight line, right? It's kind of obvious. But waves seem to travel in circles, at least certainly the waves that people knew about at the time. If I go and chuck a rock in a pond, for example, I see the waves travelling out in circular fashion. And so people thought that light couldn't be waves due to this curvature issue. And that was really the big reason why Newton himself shied away from the wave explanation of light. But on the other side, let me just check which laser I want. Yeah. On the other side, people thought it couldn't be particles either. And the reason was that they couldn't understand how if light was particles, how how beams of light could cross each other. You know, I'll take my two beams. Oh, this one's been playing up a little bit, my red one. Let's try my green one. I'm going to just change the battery as well. Wait a minute. All right, there's one green, there's another green, slightly different intensities, never mind. I can take them and I can cross them and absolutely nothing happens, right? They don't disrupt each other in any way whatsoever. And in fact, I don't even need two lasers. It would have been fine if I hadn't got another one to work, because actually this room is full of light, right? Just by virtue of shining this laser over there, why isn't it being disrupted from bumping into other particles of light? So this was a big reason why they thought, well, it can't be particles either. So it couldn't be waves, it couldn't be particles, they knew of nothing else, so it was all very depressing. So what about reflection? So the law of reflection was known. First mirrors are known back to 6000 BC at least. Even the law of reflection was known to the ancient Greeks at least. And so this was all known, and this is very easy to explain if you think of light as particles. It's just sort of like a bouncing ball problem, right? You just think of these little balls of light bouncing off this reflective surface. It's just a conservation of energy and momentum type argument that tells you that they should bounce off at the same angle as they came in at. So that makes sense for particles. What about refraction? That's maybe a little bit more difficult. But this law of refraction, so Snell's law, I'm sure most of you will have seen that before, was known to Newton. Snell had written it down, I think, in 1621, so it was well known. In fact, there's evidence as well, I think, to suggest it was known way, way before, in 984 AD even, but Snell gets the credit because he actually wrote it down. That's the thing, write anything down, that if you come up with an amazing idea, write it down, everybody. But Newton did have some kind of semi-plausible explanation for particles. If anyone's interested, I can tell you afterwards. It was vaguely plausible, but it also turns out it's very easy to explain for waves if they travel in straight lines, and as we'll see in a little bit. So what else was known? Diffraction effects were known about. Newton studied diffraction. So diffraction is basically the sort of deviation from straight line propagation when light passes around an object or an obstruction. As I said, we'll learn more about that next term. But Newton studied it. He came up with his now called Newton's rings experiment. You'll probably do that in labs. And we now see that as proof of the wave-like nature of light. But because Newton was so convinced with the particle theory, he largely ignored his own evidence there. The colour, so again, Newton had been playing around with prisms since he was about 23, and he knew that white light split into subcolours, but he didn't know why. He didn't know what it was about light that made it do that. He thought maybe the different particles of light, that colour was maybe just a property of different particles of light, so different particles had different colours. Polarization as well, that's very much a wave-like phenomena that we understand today. It was known about, but no one really understood it at all. So the first polarization effect that people really knew about was that from Iceland spar. It's a crystal. I've got a couple of examples down here if people want to look at it later. But some sailors went off to Iceland. They brought back these crystals. And what you see if you look through one of these crystals is that anything you look through actually has a double image. So they thought that was weird and fun. They didn't know why it was. We now know it's due to something we call birefringence. Again, that's something you learn about in the second year. Not in this course, but it's basically just that a crystal like that, a material, can have two different refractive indices depending on the polarization of the light and depending on the direction of propagation through the crystal. Okay, so at the same time as Newton, along came Christian Huygens as well, and in 1690, I think, he made this key statement in his treatise on light, and he said, "For I do not find that anyone has yet given a probable explanation of why light is not propagated except in straight lines, and how visible rays can cross each other without hindering one another in any way." So he's basically saying, I don't think anyone's explained these problems that I've just told you about, these two issues, but I think I have found an explanation. That's what he's saying. Okay, so what did Huygens say? So his principle tells us to consider each point on a wavefront as a new source of radiation, and then you add the radiation together from all these sources to get the new wave. Now, Huygens' principle makes no physical sense, right? It just doesn't. We now know that this is not the right physical model at all. So don't worry, don't get hung up on that. So we know that, but we teach it to you not only because of the historical perspective, but also because actually what we'll see is that it does actually give you the right answer, even if it's for a number of things anyway, even if it's for the wrong reasons. And it actually turns out to be a rather easy way to get the right answer, an easier way than the actual physical model. So we still teach it to you and we still actually use it. So what did Huygens actually say? So we call his model a wave-like model, but he wasn't thinking of waves or light waves, electromagnetic waves that we think of today, with crests and troughs and frequency and wavelength. He wasn't thinking of that. He was thinking more about, he talked about a disturbance. He was thinking more of a little bit more of something like a longitudinal wave, a bit more like a sound wave. So he talked about a series of pulsations in the ether. Okay, so what is the ether? Many of you have probably heard of the ether, but it was a popular idea at the time because the waves that people knew about at the time all needed some kind of medium in which to propagate. So sound waves need air, water waves need water. So they couldn't understand, for example, how light from the sun can reach us through the vacuum of space unless there was some medium permeating all of space. So they called this the ether, and that was a popular idea. So he thought of, so Huygens imagined sort of disturbances in the ether. He thought, right, the particles of the ether, let's just set one of them sort of, vibrating, and as it does so, it sort of sets other ones vibrating around it, and they set other ones vibrating around that, and so on and so forth, right? And so he thought that was the way in which light could be propagated, and he thought that light for us is caused by some kind of interaction of the ether with our eye, such that if the ether is vibrating in some coherent way, we see that and we call it light, right? That's what he thought was going on. So it's complete nonsense in terms of actual reality. But what it did do was lead to a geometric construction, which actually, as we'll see, does allow us to get the right answers. So this is the first box. I think this is possibly the only box that is words rather than mathematical derivations. I think, we'll see. So this is a definition. It's probably about 5 lines or something you'll need. Of course, if that isn't quite big enough for you, supplement with extra paper. So what Huygens construction is, and you may, so in an exam, for example, you could be asked what is Huygens principle or what is Huygens construction. Those phrases are interchangeable. So this is what you need to write if you are asked for either of those things. So he said that every point tell me if anything's too small and you need me to, write big or anything. So he said that, right, every point on a wavefront may be regarded as a source of secondary wavelets. What is a wavelet? Well, it's sort of like a little wave, but you can't see it, essentially, which spread out with, go on to the next board, with the wave velocity. For me, it's a bit bigger than 5 lines, sorry, because I'm trying to write big. And then the final bit is the new wavefront is the envelope or the tangent of these secondary wavelets. Okay, so that's his construction. Well, that's what he said one should do to get the answer. And so let's just have a quick look at what he meant. So this red line is supposed to be representing the front of some wave, this wavefront, and you can put a load of points along it, all of which are a source of these secondary wavelets. That's what those black circles are supposed to be. And then the wavefront at some later time, you get just from taking the tangent, essentially, or the envelope of these wavelets. So that orange line represents the wave at some later time, where it is at some later time. So this has some nice properties. Straight wavefronts stay straight, so this seems to be solving this whole straight line thing, except if, okay, you look at the edges, so let's not look at those too closely at the moment. Okay, let's brush that under the carpet. And the other thing he said, and this really is the right way to look at things, is that points on the wavefront all move forward at the same speed in a direction normal to the wavefront. Okay, so what that means as well is that all points on a wavefront correspond to the same point in time. So any point along either of these red lines shown here, they just represent where the wave has got to at a particular point in time. And then the actual direction of the light is perpendicular to that, and we tend to represent that by these arrows or lines, these light rays. And as we go on, you'll see that some of the pictures I start to draw, I will start not bothering to draw the wave fronts. I will just be drawing the rays to represent the direction of propagation of the light. Okay. Right, there's a couple of problems with this. One of them I sort of already slightly highlighted. Okay, so the first one is, why would these wave fronts only travel forwards and not backwards? We know that light does travel forwards, but actually, according to this model, oh, sorry, I've gone the wrong way. According to this model, why wouldn't these little black circles also start spreading out behind? You know, the model itself doesn't really explain that. Also, what's going on at the edges, you know, this sort of slight business over, you know, at either side is not really explained by the model either. Well, okay, later on, Fresnel and Kirchhoff, I'll write their names just in case you want to go and look it up. So they came along and developed a slightly more serious model, and they, you know, which explains these features. So you can do that, you can fix up the model. But number one, it's, okay, sorry about this phrase because I'll probably use it a lot, but it's beyond the scope of this course. But probably moreover, actually, in some sense, there's no point fixing up a model that you know isn't the right one anyway, right? So we use Huygens' construction in its sort of simplest, purest form, just to give us the right answers for simple problems. And it's not only because you know, you're first years and we think, let's make it simple. It's not that at all. It's actually, this is really a very useful construction, and even modern computer simulations still use Huygens construction to get the right answers because it's a very quick and very easy way to do it. If you wanted to do it properly, you'd have to wait for a couple of 100 years for Maxwell to come along, and you'd have to solve Maxwell's equations. You'll learn about Maxwell's equations in electricity and magnetism, but you'd have to solve those, and you'd have to solve them in multiply bounded regions, and it swiftly becomes, you know, very, very complicated. So we do it this way because it gives us the right answer. So it's not just historical, it is actually useful as well. Okay, so how does reflection work according to Huygens' principle? So here we have a wavefront coming in with this red line. Remember, the direction of propagation of the light is actually perpendicular to that. I've just not drawn the rays on this particular diagram. So the wavefront comes in, it hits this medium, this reflective surface in this case, and Huygens says that as it does so, it becomes a source of secondary wavelets. Okay, these wavelets can't actually penetrate the medium, so they have to go back out again. You might have been making it up, I don't know, but anyway, out it comes again. And these wavelets, because these are, oh, right, so the new wavefront is the envelope of these wavelets, as we've just said. And because these wavelets are traveling in air just the same as the incoming wave, then they're all growing at the same speed. Right? And so we'll do the geometry in a minute, but hopefully you can intuitively see that that must mean then that the wavefront is coming out at the same angle as the incoming one was going in, if you see what I mean. Right. So I think I'm just repeating what I've just said there here. So yeah, so the incoming wavefront is at the same angle as the outgoing wavefront. Also, therefore, the incoming ray is at the same angle as the outgoing ray. And this all occurs precisely because the secondary wavelets grow at the same rate in both wavefronts because they're both in air. Okay. Is everyone happy up to this point? Okay, so we're actually going to do the geometry. I mean, probably you've already been able to intuitively see that it must be true that the angle of incidence is equal to the angle of reflection, but we're just going to do it in a bit more rigorous calculation way now. But let me try and explain so the actual maths is 5 lines, 4 lines, something like that. But let me explain this diagram first, because that's probably the most complicated bit about what's going on. So, right, so, okay, do stop me if this isn't clear, because this is a messy diagram. Okay, so the wavefronts are being represented by the red lines. So this is the incoming wavefront, okay? And the green are the rays, so they're always perpendicular. The green is always perpendicular to the red, okay? Right, so what's happening is that this particular wavefront that I've drawn, this side of it is just starting to hit this reflective medium. And as soon as it does so, it starts generating secondary wavelets, right? And I've just drawn one of them here, just to try and make the diagram just a little bit less messy. Okay, but as soon as it hits, out come these secondary wavelets. One of them is being drawn here. This point B, so as this is happening, as these wavelets are coming out, this point B on the wavefront is still travelling down here, okay? And at the point it hits the medium as well, it will start to generate wavelets as well, right? Now, the wavelet that I have drawn here is the one that has come from A at the same time as this edge of the wavefront hits B prime, right? Let me write one bit of maths, which is to put in the box, which I hope will make that clearer. And we'll just check, right. So what I'm saying is that the length A prime, that is the radius of this particular wavelet that I've drawn, is equal to the length B prime, and it's equal to VT, where that's the speed of the wave, and that's the time for A to get to A prime, or equivalently B to get to B prime. Right, so does that make sense? So that length AA prime is the same length as BB prime because it's taken the same amount of time for the wavelength from here as it has for B to then get to B prime. Does that make sense? So B prime is just generating its own little wavelet, just starting to. So what I've done is drawn the tangent, and that has become the new wavefront. Okay, so that other red line is now my outgoing wavefront. Okay. From there, I'm going to pause because this is almost the hardest bit to get of this diagram. Now it's just going to be geometry. So is everyone clear specifically on why that is my new outgoing wavefront? Okay. I don't see any no's, but you can. Okay. Right. So then geometry. If you just look at that diagram, what you can see is that length AA prime is equal to, I've not defined the angles, right? Let's do that first before I do anything else. Right, so we always define our angles as the angle between the normal to the surface and the ray, right? So this theta I is the incident angle, and with a bit of geometry in your head, you'll also see therefore that is also theta I. And then this one, the reflected angle, again defined with respect to the normal. That's theta r, and a bit of geometry in your head will show you that must also therefore be theta r. So then what I can write is that is true, and also that is true. And since, due to the fact that the wavelet grows at the same rate as the incoming wave moves, I know that those two things are equal, and so that gives me the law of reflection, but of course usually just written like that. Okay, so that's the law of reflection, that the incoming and the reflected angles are the same. So that is the proof based on Huygens principle. Construction, sorry. Okay. Is everybody happy with that? You can get marks for sort of reproducing this kind of thing in a prelims exams. Okay, so we can use those ideas just to think about a few things. For example, how an image is formed in a mirror. So here's just an example. We'll talk a lot more about images later on. But here's a light source over here. So a light source is just something that spews out light rays, right? It could be the lights in this room, it could be the sun, it could be you. You're a light source as well, because light impinges on you, you reflect it out, so you can be a light source as well. That's how I can see you. Okay, so these light rays, don't worry about the colours, that doesn't mean anything, they're just 3 different rays. So in they're coming at various different angles, obviously being reflected out at the same angle as they came in at. Here's our eye, and just to make things simpler, I've just put a screen just to block my direct view to the object so that all I concentrate on is the image itself. So what your eye sees are these diverging, or apparently diverging light rays, and your brain tracks them back. So that's what's represented with these dashed lines or dotted lines. And it appears to your brain eye system that these light rays have come from a point here. So this is your image. It's a virtual image in this case because no light rays really do cross there. It just appears to you as if they have. So you see that image, and it sits, of course, for this flat mirror at the same distance behind the mirror as the object does in front. So that is how a mirror works. Probably you all knew that anyway. And we'll talk a lot about more about real and virtual images later on, but it's sometimes good to see this sort of easy example at the start. Okay, what about refraction, according to Huygens? Okay. So, turns out refraction is quite easily explained if wavelets travel more slowly in the medium, so glass, for example, than in air. So, again, I've drawn a few wave fronts coming in, these red lines. So what you see is that, let's concentrate on this third one from the top. So this one's about to hit this medium, this denser medium. And it starts, as soon as it does, it starts generating wavelets. The other end of that same wavefront is also generating its wavelets. But the space between these wavelets is bigger because the wave can travel faster in air than it can in glass. Okay? So the key thing to remember is that these green lines that I'm showing here represent the same amount of time, right? So that end of the wavelet gets to there in the same amount of time that that end of the wavefront gets to there. And just the different spacing between the wavelets is just indicating how fast the wave can go. Okay, so we can derive Snell's law now, or the law of refraction, by just cutting this diagram down to its basics. So what have I done here? So I've drawn the last wavefront that is about to enter the glass, so the last wavefront that's fully in air, and then the first wavefront that's fully in glass. I've put on some construction lines to help us. The blue lines here represent the rays, and then I've put on some angles as well. Right, so there's your incident angle, again, always defined between the normal and the incoming ray. Can you in your head sort of do, well, that one's easy, but can you in your head just check that you're happy that that therefore is also θ1. And then I've done the same thing here. This is θ2, the refracted angle, meaning that that angle there, as well as that angle there, is also θ2. So you're happy with the picture? Okay. Okay. So, right, so to repeat again, because this is really the key thing. The light ray takes the same amount of time to travel this length d1 as it does to travel d2. Remember, I said any point on the wavefront represents the same instant in time, essentially. And we also know that the light travels at different speeds in the different media. Probably you've seen this before, but in general, in a medium of refractive index n, the speed of the wave is given by c over n, where in this case we've just got two different media, where c is the speed of light in a vacuum. So c is the largest value of the speed of light you will ever see, and in any medium, it travels more slowly. Okay, so what to put in the box? Right, so what we're saying is that the time taken to travel d1 is the same as the time taken to travel d2. Also then using that in a minute. And the other thing we know is that d1 equals d sine θ1, and d2 equals d sine θ2, means that using also our expression for the v's, therefore we know that d sine theta 1 n1 over c equals d sine theta 2 n2 over c. Some constants cancelling out both sides, and then therefore you've got Snell's law. So that is Snell's law, or the law of refraction. And again, reproducing that can get you some marks in an exam. Everybody happy with that? Okay, just brief interlude. Just to show you some sort of typical refractive indices of some natural materials. So in a vacuum, the refractive index is 1, and that, of course, is when the speed of light will be c, what we call c. In air, very, very close to 1. You can just see it's a tiny bit higher than 1. In any questions you get, you will be expected to just use n equals 1 for air, right, unless you're told otherwise. But even that, it's not a precise value because it can depend on air pressure, humidity, temperature, and so on. Of course, variation in those things gives you effects such as mirages, for example. Water, typically about 4/3. It will usually be given to you as 4/3, but again, dependent on whether it's salt water versus fresh water and so on. Typical window glass tends to be about 1.5, 3/2, but again can vary. And then gemstones as well tend to have lovely high refractive indices. And there's a problem in the problem sheet as well that asks you to think a bit about that and why that is part of why they are so sparkly, right? So it's the high refractive indices that you want. Can you go higher than that? Yes, there are some natural materials that have refractive indices in the range 4, 5, 6, but they tend to be non-transparent as well, so they're not interesting in the context that we're talking about. And then there's a whole branch of physics, material science, working on metamaterials, where you can have very, very high, very, very low, even negative refractive indices, and they are really quite, so it's all man-made, very deeply exotic materials. They're quite fun. They're the sorts of materials you'd need, for example, to make an invisibility cloak, should you want to do that, to bend the light around the object rather than it ever being able to be reflected. So obviously not on syllabus, but go away and read about it if you're interested, because everyone wants an invisibility cloak, don't they? Right. Okay. Now I've got just over 5 minutes, nearly 10 minutes, to just start on talking about Fermat's principle instead. Can I check who has heard of Fermat's principle of least time? Yeah, I would say maybe about half of you, maybe not quite half, but okay, a good few of you. I imagine nearly all of you have heard of Huygens' principle. Had you? Hands up. Who had heard? Oh, that looks fewer. Is that just because you can't be? No. Okay, so Fermat's principle of least time. So Pierre de Fermat was really an amazing mathematician and physicist back in 1600s. And he was responsible for essentially rewriting all of mechanics and optics from a different viewpoint. And you will come across this in mechanics as well. I think it's in not until Hilary term, but you know, you'll hear of a general principle of least action, or strictly principle of stationary action, it should be called, for which Fermat's principle of least time was a guiding principle. So basically what he said was that light will take the path between any 2 points that takes the smallest time. Now we actually do understand why this is the case now in the context of quantum mechanics. As far as I know, Fermat himself did not have a physical model. He may have had a philosophical model for why this might be the case. Don't think he had any physical model. Now we do understand it in the context of quantum electrodynamics, and maybe if you take the right options later on, you'll learn a bit about it. If you want to know more, there's a nice little explanation. It's a bit hand-wavy, but also quite nice and intuitive, that you can find in the Feynman lectures, somewhere in volume 1. I forget which section, maybe 26, something like that, which sort of explains why this should work. But anyway, Fermat himself, I don't think knew. There's also evidence that the basic idea was probably known long before this, maybe even as early as 100 AD. Certainly 1,000 years ago, it was known by Ibn al-Haytham, who was sort of the father of a lot of modern optics, but all his works kind of got lost. So anyway, so Fermat gets the credit. And again, similar ideas will be seen in mechanics, as I said. So maybe we can at least get to looking at how reflection works. Refraction may have to wait till tomorrow. So, okay, so what Fermat said. So here's our problem, right? We've got 2 points A and B. We want the light ray to get from A to B via the mirror, right? We constrain it to go via the mirror. And we want to know, will it go via the red path or the green path or the blue path or something else that I haven't drawn, right? And what we know from Fermat's principle of least time, it was later corrected to be Fermat's, so it was later, his original statement, I should have said, his original statement what has now been modified because actually what we now know is that the path must be a local extremum. Usually it does turn out to be a minimum, but in principle it could be a maximum or inflection point as well. Anyway, but let's talk about it as he formulated. We know that the light ray takes the shortest path between these 2 points via the mirror. Okay. Now, I think it'll probably be obvious to you without doing any maths that it is going to be the green path, right? And anyway, we've already derived the law of reflection. We know the answer. Okay. One thing I have also assumed in even drawing this diagram at all is that the refractive index of air is constant. We're going to take it constant. Does anyone know why I'm saying that that's an assumption, even in just the way that I've drawn this diagram?
Otherwise, the light rays wouldn't even be straight.
That's right, exactly. So the fact that n is constant, if you look at that v equals c over n, if n is constant, then the velocity is constant, and that means that the shortest time also equals the shortest distance, and we know that the shortest distance is a straight line. Actually, if n varied, it could be some curve or something else, and we'd have to even formulate what that path should look like in that way. Anyway, n is constant in my problem, so it's going to be some kind of pair of straight lines, but which pair is it, is the problem we're now going to solve, right? Okay, so let's do this on the next slide. Okay, so what we need to do is minimize the total time, but here it is equivalent to the total distance for the reasons I've just explained, that we're assuming n is constant. Of course, you could have a more complicated problem where it's not, and then you'd have to do something a bit more complex. But anyway, this is what we're doing. So in the box, let's write down an expression for, I'm going to write it as the distance. If you really prefer to write it in terms of time instead, just imagine you're dividing everything I'm writing by a c, speed of light in air or in a vacuum. Right, so s is representing my total path length. So I've got my 2 points A and B. I happen to have labelled them to be a distance, a vertical distance y. No reason at all why these need to be the same values of y. It will work anyway. And then this is an arbitrary path. So this x is going to be variable in my problem, but is constrained such that A and B are a total constant distance A away from each other. Okay. So that's the length of the first leg of the path. This now that I'm writing is the length of the second leg of the path. And what I want to do is minimize that with respect to my variable x. If you spot a mistake, please shout, because it's always very difficult being so close to the board seeing any mistakes. So already made one, right? Plus a half, right, a minus x, a minus x squared plus y squared minus half. Right, I'm going to try and squish it in, 2a minus x, and then a minus 1 coming from that. Was there a whisper? Did you see a mistake? So that is therefore x over x squared plus y squared to the half minus a minus x over okay, a minus x squared plus y squared to the half. Okay, and I need to set that to, well, I'm not going to set it to 0 yet, because I'm also going to notice one other thing, which is that that first term is simply sine theta 1, and that second term is simply sine theta 2. And I'm setting that to 0 because I want to find the extremum, which does turn out to be a minimum in this case. And so this is giving me the law of reflection. Actually, I called it I and R, didn't I? Up on the, have I called it I and R? Let's do that. So theta incident equals theta reflected, as we saw before, of course, from Huygens as well. Okay, so just one more thing. That was an extremely laborious way of proving that, but I wanted to show you the maths. You know, what you're doing, you're just minimizing the path length with respect to the variable. But of course, actually, we could have very easily instead used sort of, oh, that's terrible. That's supposed to be a horizontal line, sorry. We could have very easily instead used some sort of geometric insight to know immediately which was going to be the shortest path. Let's say we didn't reflect it up, but we just reflected the point B down, right? So that's sort of the image of B. But of course that length is going to be exactly the same as that. And I think there you can see that that is clearly going to be shorter than a path that went something like that, and so on, right? So you could have used the geometry to know immediately that that was going to be the right path. Okay, so I think that takes us to the end. We will carry on with Fermat and do refraction tomorrow and continue on with some other problems as well. So thank you very much. Pointer if you want it. Oh, okay. Yeah.